Okay, guys, today we're going to be looking at sets of numbers. And the basic idea here is each set of numbers will be what type of number it is. And I'm going to apologize in advance. I have a new puppy here with me who, is maybe chewing on some things and maybe whining a little bit. So if that is distracting, I apologize. So this is what type of number each thing is, because within the different sets of numbers, all the numbers have similarities. So we're going to start out with like the smallest, most basic set of number, and these are the numbers that you should have learned about when you were in elementary school, and these are the natural numbers. And some of the sets of numbers are important enough that they get a letter that goes with them. This one gets an N with like a double line in the middle. And so if you ever see this N, this also means the natural numbers. And what these numbers are sometimes they're referred to as the counting numbers. It's the ones you would have learned about when you were in kindergarten. 1, 2, 3, ... Now, are they just small numbers like that? No. An example would also be something like 564. That is also a natural number. So those are natural numbers. Things that are not natural numbers would be like negative 5.2. So these are the natural numbers. And what we're going to do is we're going to, each additional set, if it adds on to it, I'm just going to describe it as what it also contains. So the whole numbers are all the natural numbers. So whole numbers are all of the natural numbers, but we're going to add in 0. So 3 is a natural number, but it is also a whole number. But 0 is a whole number, but not a natural number. And so we're going to write it like this. So for example, 53 is a whole number. It's also a natural number, but so is 0, right? So these are some whole numbers. Okay. Adding into this, we're going to bring in the integers, and the integers are important enough that they get their own letter also. The symbol for the integers is a Z. And if I had to guess, I don't remember why Z goes with integers, but I would bet it comes from a different language, like maybe German or something like that. So the integers, we use Z for it. You would think we would use I, but we don't. And the integers are going to be all of the whole numbers. So it's going to be part of this whole group. But we're going to add in negative whole numbers. So we're going to add in, so examples would be things like, 5, 22, 0, just like before. These are also integers, but also negative 3, negative 28. Something that is not an integer would be like 5.3 or negative 10.7, because these are not negative whole numbers. They're not positive whole numbers. So these are the positive or negative whole numbers. Something that is an integer that may not look like it is 10 halves. This might look like this is an integer because it's equal to 5. But something that is not an integer would be like 10 thirds, because this is 3.33333. It's not a whole number. So this one is, but this one is not. So the integers include all of these other ones. Everything that is a natural number is also a whole number and is also an integer. Okay? Our next set is going to be rational numbers. And rational numbers, this word comes from the word ratio, and it's all numbers that can be written as, so can be written as P over Q, where P and Q are integers. So if you can make a number by dividing two integers, it's called a rational number. And this is important enough that it gets its own letter. Its own letter is going to be Q. double line here. You'll notice there's always like a little double line. Sometimes this is written like with like a double line like this, but it's a Q. And so we've got natural numbers, whole numbers, integers, rational numbers. Now let's look at what rational numbers includes. It may not be obvious right away, but all integers are rational because you could do it by, you could make any number, like for instance, the number -20 can be made by dividing two integers, because you could just do -20 divided by 1. You can always divide by 1, and so all integers are also rational numbers. But now we include things like 5/3. Even though it's not a whole number, it is an integer. We also include things like decimals. -5.2 is an integer, or sorry, is a rational number because it could be rewritten as -52 divided by 10. So anything with a decimal point that ends, so fractions, decimals that we call it terminate is when they end, terminate, and repeating decimals are all rational numbers. So another example would be like 5.33333333. When you have a repeating number, it can be made by dividing by a 9. So this would be like, okay, let me see if I can do it right in my head. I think this is like 48/9. I wish I had it. Do I have a calculator? I think I brought my calculator. I think 48/9 will be 5.33333. Let's see. There's a way to simplify that. I guess I could have done that. 48/9 is 5.33. Sorry, I have my mode on only 2 decimal places. Let's do it again. 48/9, and there it is. There's that 5.33333. And you can do that for, it doesn't have to be a single repeating decimal. You could have like 0.717171, where the 71 repeats, and that's 71 divided by 99. And so anytime you have repeating decimals, that's also a rational number. So all natural numbers and whole numbers and integers can be made by dividing by 1. And all fractions, decimals that end, and repeating decimals are also all rational numbers. Oh, sorry about that. X. Okay. Now, this is the first type that is not made up of the other ones. It's going to be its own set. Irrational numbers are just the numbers that cannot be written as P over Q, where P and Q are integers. And this would include things like pi, which is a decimal, but it does not repeat. 3.14159265358979323, whatever. 3238462643383. It keeps going, but it doesn't repeat. And this cannot be rewritten. It can't be written as P over Q, although they tried really hard for a long time to write pi as P over Q. Another one we're going to learn about coming up later this semester is E. This is important enough that I'm going to tell you about it right now. It's approximately 2.718281828, which kind of looks like it's going to repeat, and then it doesn't. 4590, 4523, ... keeps going. So this is going to be really important later this year. Pi E. All square roots that are not exact numbers, like square root of 2 is what number times itself gives you 2. It's like 1.41421, I don't know. It keeps going and it doesn't repeat. Let's see, did I get that right? I don't know. Square root of 2, 1.4142135, whatever. All square roots that are not exact square roots are irrational numbers, but be careful, because if it's a square root that is exact, like square root of 25, that's also equal to 5, and so square root of 25 is a rational number. It's in fact a natural number. So irrational numbers are their own separate group. The ones from before are not. Notice it's its own different box. All the other ones were contained in each other, but irrational ones are not. However, together, irrational and rational numbers, if we add these two groups together, this is the set of all real numbers, is all of the irrational numbers and rational numbers put together, and we write that with an R with a double line at the beginning. So all the real numbers, and this is all the numbers you should have learned about before today, are either rational or irrational. Okay, but today we're going to learn about a new set of numbers, which is and we're going to learn about them more and more over the next few days. These are imaginary numbers. And I really just like the name because they have some very real-world applications. Anything involving electricity and magnetism it ends up being modeled very well by imaginary numbers. Waves end up being modeled very well, like cell phone waves and things. Like a lot of the things we really depend on today use imaginary numbers. And if you go into like electrical engineering, you use them all the time. And there is one special imaginary number that I'm going to write here, and it is the square root of -1. And we write this one as I. Now, think about this for a second. This is saying what times what equals -1, right? And if it's the square root has to be the same number, and a positive times a positive would give you a positive, but a negative times a negative would be a positive. So how are you going to do the same number times itself to get a negative number? Well, it turns out that we're going to use I for the number that when you multiply it times itself, sometimes we'll say I squared is -1. You know, like, check this out. Sometimes kids will say like -1. Well, -1 times itself, that's how we do a square root, is +1. +1 times +1 is also +1. So how are you going to multiply a number times itself to get a negative? Well, there's actually a button in the bottom of our calculators. It's this blue I, so we have to press second to get to it. And if you do I times I, that is -1. Or we could write I squared as -1. So it's the imaginary number that is the square root of -1. And it's fairly important in math when you get up to higher levels. And I just want to show you that, in fact, all square roots of negative numbers, so imaginary numbers are square roots of negative numbers, and all square roots of negative numbers, so like square root of -9, can be rewritten just using I. And the reason is we can rewrite it as square root of a positive number times square root of -1. That will be square root of -9, and then we can just do the square root. Square root of 9 is 9, square root of -1 is I. Oh, that's wrong. Sorry. Square root of 9 is 3. And square root of -1 is I. And so we're saying 3I, this is saying 3I times 3I will give you -9. And that's true because 3I times 3I will be 3 times 3 is 9. I times I is -1, and that's -9. So if we do 3I squared, that is the number you can square to get a negative number. Now, again, how are you going to multiply the same number twice to get a negative? A positive times a positive gives you a positive. And if this were a negative number, a negative times a negative would also be a positive. So we have to use imaginary numbers when we use square roots of negatives. And we'll be learning about them more over the next few days. But suffice it to say, anytime you have a square root of a negative, even if it doesn't go in, even if the square root isn't even, we can write it as the square root of a positive times I. So imaginary numbers are square roots of negative numbers. Together, imaginary numbers, they're separate from real numbers. There are no real numbers that are imaginary. There are no imaginary numbers that are real. But together, these are part of the complex numbers. So complex numbers are all numbers that can be written as A plus b times I, where a and b are real. So this is called the real part, and this is called the imaginary part, because it's getting multiplied times I, the imaginary number that is the square root of -1. And so this includes all real numbers, because it's like all real numbers plus 0 i's. This would be real. If you do 0 plus anything times I, this would be imaginary. So all real numbers can be rewritten this way, and all imaginary numbers, and some things that are mixed together. So 5 plus 3i is not real because it has an I in it, but it's also not imaginary. It is only a complex number because it's written as something plus something I. Now, sometimes if we're being sloppy, we'll just say, hey, this is imaginary, meaning it's not real. But if we're being specific, we would say that this is a complex number, not a real nor an imaginary number. Okay, so let's see how we're going to use this in the stuff we've been. How does this relate to what we've been doing? Well, we learned about the quadratic formula. And so this is a great time to see if you remember the quadratic formula. Can you write it down? And hopefully you're able to write down x equals -b plus or minus the square root of b squared minus 4ac all over 2a. And so there is our quadratic formula. So hopefully we remember it. We need it. And this involves square roots. And so what's going to happen is last class we learned how to simplify square roots. But what if the square root involves a negative? What if it involves like square root of -64? Well, this is an imaginary number. And it'll make all of the solutions not real. So let's see how that affects things. Let's say we have the equation x squared plus 9 equals 0. And we want to do the quadratic formula on this. So we would say, so in this case, a is 1, b is 0, there's no x's, and c is 9. Let's do the quadratic formula. -b, so -0 plus or minus the square root of 0 squared minus 4 times 1 times 9 all over 2a. 2 times 1. A was 1 here. So let's start simplifying this. When you have 0 plus something, you don't need to write it. It's just going to be plus or minus the square root of 0 squared is 0. 0 minus 4 times 1 times 9 is 36 all over 2. So we get plus or minus the square root of -36 divided by 2. This is the square root of a negative. It's imaginary. And so what is it? What are we going to do here? Well, we're going to start by splitting. Let's simplify the square root of -36. We're going to split it up into the square root of 36 times the square root of -1. And we'll always split it up into the square root of -1 because this can be simplified to be what number? This is I. It's the imaginary number that is the square root of -1. And then we can just do square root of 36. If you can do it, great. In this case, the square root of 36 is 6. That's just 6 times I, which we write as 6i. So this is 6i over 2. 6i divided by 2 is 3i. So that is the number that when you put it in here makes the equation true. If I do 3i squared and add 9, that will give me 0. It will make this equation true. And the reason that is because 3i squared is -9. It is the square root of -9. So that's a solution to a quadratic. Now, what if we had something like y equals x squared plus 9? Remember that we talked about how the roots of a quadratic, the solutions, the things where this is equal to 0 are the x-intercepts. So x-intercepts are the solutions. Well, if we have something like x squared plus 9, it's shifted up by 9 and there are no x-intercepts. If the solutions are where it's equal to 0 are imaginary. There's like, okay, great. I mean, that kind of makes sense. There are no real solutions because the the quadratic is never crossing the x-axis, and when we try to solve this equation, it's never true. So we have something that like kind of demystifies all of this, and it's going to be part. So again, this is a great time to see if you remember the quadratic formula. If you don't know it, this is a good time to just pause this video and go memorize the quadratic formula. Sing it to yourself, go back and look at our last video until you feel comfortable how to do it. We really need to know that the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And there is a special part of the quadratic formula that can tell us what types of solutions we are going to have. And it's called this is quadratic formula. And the special part we're going to use today is called the discriminant. And it is just the square root part. But it's not going to be the square root. We're not going to use the square root. It's going to be what's inside the square root. It's b squared minus 4ac. This is the discriminant, okay? So don't write the square root. That's the number one error I see is kids writing the square root. It's the part that's inside the square root. So you don't need to learn anything new. But the discriminant will tell us what type of solutions we have. I'm going to start out by just writing here. If b squared minus 4ac is greater than 0, if this is a positive number, then we will have two real solutions, because when you do square root of something, you'll be doing plus or minus it, and there'll be two solutions, and the square root of a positive number is real. What that looks like on a graph is when there's an equation that has y equals something, that when you do b squared minus 4ac, it'll have two x-intercepts. Okay? If b squared minus 4ac is equal to 0, then when you do the square root of it, it will be square root of 0 is 0, and when you add 0, negative b plus 0 is negative b. But also when you subtract 0, negative b minus 0 will also be negative b, and so you'll get the exact same solution repeated twice. This is one real solution. And what that'll look like on a graph is it'll look like this, where there's only one x-intercept because the x-intercept is at the vertex, okay? The last thing that could be true is the discriminant could be less than 0. So this is the discriminant, and we can just look at what sign it is. If you do b squared minus 4ac, and it comes out to be negative, so this is negative, this is positive. If it comes out to be negative, then there are two non-real solutions. They won't be real. Because when you do the square root of a negative, if you have like the square root of negative a, that's going to be square root of a times I. You're going to get an imaginary number here. And when you add an imaginary number and subtract an imaginary number, they're going to be two different solutions. The only time you get one solution is when the discriminant is 0, because adding and subtracting 0 gives you the exact same thing. But they won't be real. They'll have an imaginary part to them. And sometimes we'll just call them imaginary solutions, even though the whole number will often be complex. In this case, it was actually an imaginary number, but often it'll be a real number plus an imaginary number, but we'll still call them imaginary solutions for short. And what this looks like on a graph is if there are no real solutions, it never crosses the x-axis. There are no x-intercepts, or maybe it'll look like this. So you can tell based on the sign of the discriminant what's going on, how many solutions you're going to have. But we can do more, okay? If b squared minus 4ac is a perfect square number, so like 64 or 25 or 9, numbers that you can do the square root of and you get an exact answer. Well, if it ends up being a perfect square number, then the solutions will be the solutions. And 0 is a perfect square number too, right? So it could be one solution, it could be two solutions, depending on 0 is the only time it would be one solution. but the solutions will be rational because you're actually able to do the square root of that number, and so the numbers will come out rational. It can be rewritten as a fraction. And if the solutions are rational, it means you could factor it. This, we've been talking about factoring a lot. It turns out there are a lot of things that can't be factored, and this is a way to tell if something can be factored or not. You just do b squared minus 4ac, and if it comes out to be a perfect square, you can factor it. So, if you look at like x squared plus x minus 20, and you're not sure if it can be factored, you can do b squared, so 1 squared, minus 4ac. And if you do this, so 1 minus 4 times, it's going to be, sorry, c is negative 20. I apologize, that would have come out badly. So 4 times negative 20. And when we do this, it comes out to be 81. Can you do the square root of 81? Yes, that means it could be factored. This can be factored, and it factors into x plus 5 times x minus 4. But sometimes you'll be sitting there for a while like trying to factor something, and if you just do the discriminant on it, b squared minus 4ac, you'll end up getting times negative 19, 77. And the square root of 77 is not a perfect square number. It ends up being a weird decimal, and so those are ones that can't be factored, and you have to use the quadratic formula on them if you want to solve to see what the answers are. So if it is not a perfect square, the solutions are irrational. And so if you want to solve, you need to use the quadratic formula. What I think most people find fastest is to try for just a few seconds to factor something, and if you don't see the answer, then you be like, okay, well, let me see. I'm going to do b squared minus 4ac because I want to see if it's actually possible. And if it's not possible, then you've already done b squared minus 4ac, and so you can then go on to use the quadratic formula. So for instance, if I have x squared minus 2x minus 24 equals 0, I might look for a minute to see if I could try to factor it, like what multiplies to make 24. So 1 times 24, 2 times 12, 3 times 8, 6 times 4. And, 6 and 4 looks like it makes negative 2. So x minus 6, x plus 4 equals 0. X is 6, x is negative 4. This is a very quick way of solving it. If I can't see it right away, okay, so I'm trying to solve this one, I'm going to do what multiplies to make 25, so 25 and 1, 5 and 5. I don't see a way to make negative 2, and so I'm going to do b squared minus 4ac. So b squared minus 4ac. When I do that in my calculator, I get 104. And when I do the square root of 104, it is not an exact number, and so I know it can't be factored. But the good news is once you've done b squared minus 4ac, this is the value of the discriminant. So the discriminant is equal to 104, but that's already part of the quadratic formula. So when I start doing the quadratic formula, negative b plus or minus, I've already done part of it, and so it's not like I'm wasting my time. All over 2a. I've already done part of the quadratic formula. So once I think I can't factor, I find the discriminant, and then if it looks like I can't factor, I just keep going with the discriminant. All right, guys, hopefully you're feeling good about your sets of numbers, and you're feeling good about how to use the discriminant to help us know whether we should use the quadratic formula or not. We're going to be using both of these over the next couple of days. We're going to focus on learning more about some complex and imaginary numbers the next day. And then we're going to come back and use the quadratic formula on things that have imaginary numbers and talk about how we're going to use that. I hope you have a good rest of your day, and let me know if you have any questions. Bye.